In computer science, a lookup table is an array that replaces runtime computation with a simpler array indexing operation. The savings in terms of processing time can be significant, since retrieving a value from memory is often faster than undergoing an expensive computation or input-output operation. The tables may be pre-calculated and stored in static program storage, calculated as part of a program's initialization phase, or even stored in hardware in application-specific platforms. Lookup tables are also used extensively to validate input values by matching against a list of valid items in an array, and, in some programming languages, may include pointer functions to process the matching input. History. Before the advent of computers, lookup tables of values were used to speed up hand calculations of complex functions, such as in trigonometry, logarithms, and statistical density functions. In ancient India, Aryabhata created one of the first sign tables, which he encoded in a Sanskrit letter-based number system. In 493 AD, Victorius of Aquitaine wrote a 98-column multiplication table which gave the product of every number from 2 to 50 times, and the rows were a list of numbers starting with 1000, descending by hundreds to 100, then descending by tens to 10, then by ones to 1, and then the fractions down to 1/144th. Modern schoolchildren are often taught to memorize times tables to avoid calculations of the most commonly used numbers. Early in the history of computers, input-output operations were particularly slow, even in comparison to processor speeds of the time. It made sense to reduce expensive read operations by a form of manual caching by creating either static lookup tables or dynamic prefetched arrays, to contain only the most commonly occurring data items. Despite the introduction of system-wide caching that now automates this process, application-level lookup tables can still improve performance for data items that rarely, if ever, change. Examples: simple lookup in an array, an associative array, or a linked list. This is known as a linear search or brute force search, each element being checked for equality in turn and the associated value, if any, used as a result of the search. This is often the slowest search method, and less frequently occurring values occur early in the list. For a one-dimensional array or linked list, the lookup is usually to determine whether or not there is a match with an input data value. Binary search in an array or an associative array. An example of a divide-and-conquer algorithm. Binary search involves each element being found by determining which half of the table a match may be found in and repeating until either success or failure. This is only possible if the list is sorted, but gives good performance even if the list is lengthy. Trivial hash function. For a trivial hash function lookup, the unsigned raw data value is used directly as an index to a one-dimensional table to extract a result. For small ranges, this can be amongst the fastest lookup, even exceeding binary search speed with 0 branches and executing in constant time. Counting bits in a series of bytes. One discrete problem that is expensive to solve on many computers is that of counting the number of bits which are set to 1 in a number, sometimes called the population function. For example, the decimal number 37 is 00100101 in binary, so it contains 3 bits that are set to binary 1. A simple example of C code designed to count the 1 bits in a int might look like this. Int count underscore ones, int result equals 0, while result plus plus, x equals xn, return result. This apparently simple algorithm can take potentially hundreds of cycles even on a modern architecture, because it makes many branches in the loop, and branching is slow. This can be ameliorated using loop unrolling and some other compiler optimizations. There is, however, a simple and much faster algorithmic solution, using a trivial hash function table lookup. Simply construct a static table, bits_set, with 256 entries giving the number of 1-bit set in each possible byte value. Then use this table to find the number of ones in each byte of the integer using a trivial hash function lookup on each byte in turn, and sum them. This requires no branches, and just 4 indexed memory accesses, considerably faster than the earlier code. Int count_ones, return bits_set, x and 255 plus bits_set, and 255 plus bits_set, and 255 plus bits_set, and 255. The above source can be improved easily by recasting x as a 4-byte unsigned char array and preferably coded in line as a single statement instead of being a function. Note that even this simple algorithm can be too slow now, because the original code might run faster from the cache of modern processors. And lookup tables do not fit well in caches and can cause a slower access to memory. Lookup tables in image processing in data analysis applications, such as image processing. A lookup table is used to transform the input data into a more desirable output format. For example, a grayscale picture of the planet Saturn will be transformed into a color image to emphasize the differences in its rings. A classic example of reducing runtime computations using lookup tables is to obtain the result of a trigonometry calculation, such as the sign of a value. Calculating trigonometric functions can substantially slow a computing application. The same application can finish much sooner when it first pre-calculates the sign of a number of values. For example, for each whole number of degrees. When the program requires the sign of a value, it can use the lookup table to retrieve the closest sign value from a memory address, and may also take the step of interpolating to the sign of the desired value, instead of calculating by mathematical formula. Lookup tables are thus used by mathematics Go processors in computer systems. An error in a lookup table was responsible for Intel's infamous floating-point divide bug. Functions of a single variable may be implemented by a simple array. Functions involving 2 or more variables require multidimensional array indexing techniques. The latter case may thus employ a 2-dimensional array of power x, y, to replace a function to calculate x, y for a limited range of x and y values. Functions that have more than one result may be implemented with lookup tables that are arrays of structures. As mentioned, there are intermediate solutions that use tables in combination with a small amount of computation, often using interpolation. Pre-calculation combined with interpolation can produce higher accuracy for values that fall between 2 pre-computed values. This technique requires slightly more time to be performed but can greatly enhance accuracy in applications that require the higher accuracy, depending on the values being pre-computed. Pre-computation with interpolation can also be used to shrink the lookup table size while maintaining accuracy. In image processing, lookup tables are often called LUTs and give an output value for each of a range of index values. In computed tomography, windowing refers to a related concept for determining how to display the intensity of measured radiation. While often effective, employing a lookup table may nevertheless result in a severe penalty if the computation that the LUT replaces is relatively simple. Memory retrieval time and the complexity of memory requirements can increase application operation time and system complexity relative to what would be required by straight formula computation. The possibility of polluting the cache may also become a problem. Table accesses for large tables will almost certainly cause a cache miss. This phenomenon is increasingly becoming an issue as processes outpace memory. A similar issue appears in rematerialization, a compiler optimization. In some environments, such as the Java programming language, table lookups can be even more expensive due to mandatory bounds checking involving an additional comparison and branch for each lookup. There are two fundamental limitations on when it is possible to construct a lookup table for a required operation. One is the amount of memory that is available. One cannot construct a lookup table larger than the space available for the table, although it is possible to construct disk-based lookup tables at the expense of lookup time. The other is the time required to compute the table values in the first instance, although this usually needs to be done only once. If it takes a prohibitively long time, it may make the use of a lookup table an inappropriate solution. As previously stated, however, tables can be statically defined in many cases. Computing signs. Most computers, which only perform basic arithmetic operations, cannot directly calculate the sign of a given value. Instead, they use the CORDIC algorithm or a complex formula such as the following Taylor series to compute the value of sign to a high degree of precision. However, this can be expensive to compute, especially on slow processors, and there are many applications, particularly in traditional computer graphics, that need to compute many thousands of sign values every second. A common solution is to initially compute the sign of many evenly distributed values, and then to find the sign of x we choose the sign of the value closest to x. This will be close to the correct value because sign is a continuous function with a bounded rate of change. For example, real array sign underscore table -1000 1000 for x from -1000 to 1000 sign underscore table x equals sign function lookup underscore sign return sign underscore table round. Unfortunately, the table requires quite a bit of space. If IEEE double precision floating point numbers are used, over 16,000 bytes would be required. We can use fewer samples, but then our precision will significantly worsen. One good solution is linear interpolation, which draws a line between the 2 points in the table on either side of the value and locates the answer on that line. This is still quick to compute, and much more accurate for smooth functions such as the sine function. Here is our example using linear interpolation. Function lookup underscore sign x1 equals floor y1 equals sign underscore table x1 y2 equals sign underscore table x1 plus 1 return y1 plus asterisk. Another solution that uses a quarter of the space but takes a bit longer to compute would be to take into account the relationships between sine and cosine along with their symmetry rules. In this case, the lookup table is calculated by using the sine function for the first quadrant. When we need a value, we assign a variable to be the angle wrapped to the first quadrant. We then wrap the angle to the 4 quadrants and return the correct value. For cosine, we only have to return the angle shifted by pi 2. For tangent, we divide the sine by the cosine. Function inish underscore sine plus 1 sine underscore table x equals sine function lookup underscore sine x equals wrap x from 0 to 360 y equals mod if return sine underscore table y if return sine underscore table 90 y if return sine underscore table y return sine underscore table 90 y. Function lookup underscore cosine return lookup underscore sine function lookup underscore tan return lookup underscore cosine. When using interpolation, the size of the lookup table can be reduced by using non-uniform sampling, which means that where the function is close to straight, we use few sample points, while where it changes value quickly we use more sample points to keep the approximation close to the real curve. For more information, see interpolation. Other usage of lookup tables. Caches. Storage caches work also like a lookup table. The table is built with very fast memory instead of being stored on slower external memory, and maintains 2 pieces of data for a subrange of bits composing an external memory address. One piece contains the value of the remaining bits of the address. If these bits match with those from the memory address to read or write, then the other piece contains the cached value for this address. The other piece maintains the data associated to that address. A single lookup is performed to read the tag in the lookup table at the index specified by the lowest bits of the desired external storage address, and to determine if the memory address is hit by the cache. When a hit is found, no access to external memory is needed. Hardware LUTs in digital logic. An n-bit lookup table can be implemented with a multiplexer whose select lines are the inputs of the LUT and whose inputs are constants. An n-bit LUT can encode any n-input Boolean function by modeling such functions as truth tables. This is an efficient way of encoding Boolean logic functions, and LUTs with 4 to 6 bits of input are in fact the key component of modern field programmable gate arrays.